Okay, welcome everybody. This is Steve Hill. I'm the CEO of New Hydrogen, and I'm here today with Dr. Chengzhang Wan, who is a key team member of our sponsored research program at UCLA. And welcome, Chengzhang. It's good to have you here.
Hi. Yeah.
We're here today to talk a little bit about the Nature Materials article that was published a couple months ago, where you were a principal author in the research. And I was wondering if you could give us kind of a quick summary. New Hydrogen is sponsoring the research over at UCLA, and you guys have been doing great work. And I wanted to see if you could kind of give just why would anybody want to know about this? What's the big deal? What did you find?
Okay. So, in a very brief summary, I'm gonna share some of our current ideas and the current work of our hydrogen production and water splitting, like water electrolyzer projects regarding the so-called green hydrogen production and the energy sustainable future.
Great.
So, so our work may primarily focus on how to produce hydrogen coupled with the solar energy or the wind energy. And this specific work actually focuses on designing a new structure of catalyst that can boost the hydrogen production rate in the alkaline condition by like 100 times faster than the commercial platinum carbon. And the catalyst is also based on platinum. However, because our mass activity is like over at least over 20 times higher than the commercial carbon, so actually we save a lot of the catalyst. And also our stability is much higher than the commercial one. So that means like if the commercial one can only work for 20 hours, our can work for 2,000 hours or even more.
Which makes a lot of sense in the world of, because durability is a big part of this as well, right? It's how long does your catalyst last? How long can it continue to produce
Yes.
before you need to replace? And you can't just take out the iridium and put in new iridium. You've got to, or platinum, you've got to do a whole
Yes.
new thing.
Yes. And actually, the durability is the most important thing. It's actually more important than the activity because, like the DOE set a target, like you have to only decrease like 1 millivolt per within 1 millivolt per 1,000 hours.
Mm-hmm.
And I think none of these current catalysts can reach the target. So, but they all have pretty good activity. So you know what?
Yeah. So the activity is there. It's the durability that we're looking at to try and find a way to reach those goals.
Yes.
Fantastic. And you are finding a way to do it. You mentioned the catalyst. Maybe for some of the listening audience that doesn't understand what a catalyst is, or OER versus HER, or could you give like a brief kind of basic explanation of how these things work to create hydrogen?
Okay, so we create hydrogen from water. So a water that is H2O, it contains two hydrogen atoms and one oxygen atoms. Once you put electricity in on the cathode, the water gonna be reduced to hydrogen, release hydrogen gas. On the anode, the water gonna be oxidized to release oxygen. So the total reaction is water gets split into oxygen and hydrogen. And the in the cathode, we need platinum as a catalyst. On the anode, we need iridium as a catalyst. Both of them are very expensive. So that's why we would like to develop the efficient and durable catalyst to reduce the catalyst cost from the commercialized electrolyzer point of view.
Yeah, it gets to the economics of this situation, because that's the goal here, is to lower the cost of hydrogen production, and hopefully green hydrogen production,
Yes.
to the lowest point that we can do. And one of the most expensive components of this whole black box that we're using to create hydrogen is this expensive rare earth metals that we plug in there. And so you and your team have been working on finding ways to make them last longer, to use less. Am I on the right track there with this research?
Yes.
And so when this publication then that's come out is a report on the activity that you've been up to this point. What has been the result? Or can you give some basic information about how that's been working? I know because you and we've been working together, but maybe for the rest of everyone else that we can share, how are you making it last longer? What's happening?
Okay, let me think of it, how to, explain it in a pretty uh, simple way. So, uh, you know, in the alkaline media, because the reactant of hydrogen production is the hydronium, but in the alkaline media, the hydronium concentration is much, much lower.
Mhm.
Therefore, no matter how active your PD site is, they're just that much reactant. So you cannot increase the activity. You cannot increase the reaction rate. It is the mass transport of the reactant that limited the overall activity. So in this case, we look beyond the active site. We're trying to tailor or modulate the local environment near the active site to try to create a acidic-like environment to increase the supply rate of the hydronium so that the PT can use all of his power to catalyze the reaction. So in this case, yeah, we build up a amorphous nickel hydroxide shell out of the PT core. So this nickel hydroxide cell is what is amazing of this nickel hydroxide cell is it can do two things. One is accelerate the water dissociation rate. So the water dissociate into the hydroxyl and the hydronium, or the H plus, just a proton.
Mm-hmm.
And the proton, the second thing is the amorphous nickel hydroxide shell is proton conductive. It's a solid. It's kind of intuitive, but it's solid, but it's also hydrogen conductive. I'll explain that later, but since it's hydrogen conductive, so the dissociated, the hydrogen or the proton dissociate from the water dissociation reaction, then diffuse inward from the outside to the surface of the PT, then get reduced on the PT and produce the hydrogen, and small hydrogen molecules just diffused outward to the surface and eventually be captured by accumulate and captured by our equipment. And that's how basically that works. I don't know if that.
Yeah, that helps. So correct me if I'm wrong. It's kind of like you're creating this protective shell around the around the platinum that keeps it from degrading faster or keeps it from oxidizing faster. Is that the right way to put it? So basically it's protecting the material so that it can last longer. Is that right?
No? That's for the durability part. And what I just talked about is on the activity point of view.
Got it.
Yeah. So, but your understanding is correct for the durability. Yes, it's a protecting shell. It protects the structure from dissolution, from the surface atom migration, and also from prevent the surface from the attack of cations or anions like chloride, bromide, these possible impurities from the electrolyte.
So what is the significance of all of this? Like if you're looking, just stepping back for a minute from the scientific world a little and just saying, why is this important? Yeah, obviously it's going to make it last longer. It's going to be a little cheaper, but what does that mean for industry, for meeting the goals that are set?
Okay, I see. This is a pretty good question. That is actually the driving force for our team to work on this. And so the hydrogen is a very valuable energy carrier and also chemical that be widely adopted in ammonia production, like fertilizer industry, metal refining, and a lot of things. Basically, everything used in your daily life has to be produced with the help of hydrogen. And the second thing is the traditional production of hydrogen is based on the steam reforming of fossil fuels like the oil or the methane, things like that. That create a huge numbers of CO2 each year. So that's about 800 million tons per year for produced hydrogen. There's a huge number of them. And because we know that our climate change and the temperature increases. So we have to find a way that can produce hydrogen without without any or with very little CO2 emission. And here comes the
yeah, go ahead.
here comes the green energy production. And it's actually proposed by the DOE, by the Department of Energy of US, that in the long term, we have to replace all of our steam reforming method with the green energy production, or we have to at least add the CO2 capture devices to the traditional steam reforming devices, so that the CO2 emission will not be that massive. So the green hydrogen means hydrogen produced from using solar energy or wind energy, and I think the blue hydrogen means hydrogen produced from steam reforming, but with CO2 capture. And the gray hydrogen means hydrogen directly from methane steam reforming without any CO2 capture.
And that's the magic here, I think, that you're getting to now, is the answer to the first question. The world needs hydrogen. Not a lot of us think about it on a daily basis. Why do I need hydrogen? Well, hydrogen's behind a lot of things. So you mentioned ammonia production. It's what we use to produce fertilizers to feed the world. Hydrogen is critical. It's what we use to refine oil, to manufacture steel. Heavy industry uses it, glass, pharmaceuticals. There's a lot of things that we're using this hydrogen for. But traditionally, to the second part of what you said, traditionally, we are using dirty hydrogen, right? We're using coal, or we're using steam methane reformation to convert natural gas, methane, into this hydrogen. And your team is finding a way to do this in a way that can be sustainable, that can be, because those resources are limited. Whether or not people believe in global warming or anything else, we only have a limited quantity of these things. We know we have plenty of sunlight and wind. There's problems to be solved with that too, but that's the green side of it. And the second part of it is, how do we get this action going without burning coal or using gas? And your team is on the forefront of discovering how we can modify these catalyzers. How can we improve them, these catalysts, to be able to create hydrogen in a clean way, and also cheaply, because that's the second part of it. We can do it clean, but that's $5 or $6 per kilogram today, right? And we want to get it down to $1 per kilogram or less, even if we can. But that's tricky. And looking at the important components of an electrolyzer and finding out what's costing all the money, and then improving that, like removing or reducing the amount of platinum, iridium that are in these things, and making them last longer, which is also what your team's working on. I see that as kind of the big discovery, the big reason why people should care about what you've published in Nature Materials magazine, or Nature Materials journal, is that this is really cool stuff. It's not on the surface. Most people don't recognize it. But would you agree with that summary?
Yes, and one more thing is that you mentioned about cut off the price, right? So the overall target is $1, because that's actually the price of traditional steam reforming hydrogen production. And one thing that people may not realize in the electrolyzers is that actually the water cost. We use ultra pure water to feed the electrolyzers, and the maintenance of the water recycling and water purification, it actually occupy around 10% of the total capital cost. 10%. And
so the feedstock is a big part of this cost too.
Yeah, and our catalyst, because with this protection shell, we can use seawater instead of the pure water to feed the electrolyzers. And seawater, this is everywhere, and it's basically cost nothing, especially like in California or any coastal region, right? And also we can easily couple the seawater electrolyzers with the offshore wind power plant. Mm-hmm. That's totally clean, totally cheap, and very promising.
That is super exciting stuff you're talking about, because now we're talking about a pathway forward to the future.
Yeah.
That's sustainable, that we can continue, and we're using these natural resources to do it. Plenty of seawater available. The problem, maybe you can explain quickly to other people why do we need this ultra pure water as a feedstock for traditional electrolyzers?
Okay, so three things. One is that because the seawater has a lot of chloride ions and the bromine ions, these things are corrosive to all the metallic components in your electrolyzers. And PT, iridium, platinum, iridium, they're all or metals. Although they're kind of corrosive resistant, but they're still gonna be deactivated by these anions. So the activity of PT or iridium-based catalyst in seawater is always much worse than that in the pure water. And the second thing is the membrane, but we're not talking about the membrane in our research, but membrane also get blocked and deactivated by the attack of the chloride and the production of chloride oxidation, and the product of chloride oxidation. So the membrane also deactivated. So in this time, in this regard, like the seawater electrolyzers is not active and it's not stable at all compared with the traditional one. So that's like still a long way to get commercialized, but we are working on that. Yeah.
I think that's a really good finding that you decided to use seawater as a feedstock, which I think maybe wasn't part of the original plan, was it?
It's not, but yeah.
Yeah. Well, I think it's amazing that someone thought to put it in there and give it a shot, because these are the way discoveries are made, right? And you're playing around with it and you're discovering different ways to make things happen. And you've discovered some pretty amazing things. So what's next then? You've discovered this way to produce things. We've done it at a lab scale. I know you have a prototype electrolyzer there that you can plug things into, and you can try different materials to see what happens. Now we've discovered that there is a longer life, there's higher activity, or just as good of activity with less platinum. So what happens next with your team? How does this move forward?
Well, it's a very good question. So, the water electrolyzers consist of the cathode and anode. Now we pretty much have a very good cathode catalyst, and now we are focusing on developing the anode catalyst. So the anode catalyst, as you mentioned, iridium, that is, I think that is 1.5 or 2 times higher than the price of platinum. So you don't want to use too much iridium on the anode. Probably just don't use any iridium on the anode. So our team was also developing is also developing transition metal, sheet metal based catalyst that can have comparable activity and durability as iridium catalyst. So in that case, if we can replace the iridium part from by the transition metals, then we're going to save another lot of money cost from the for the electrolyzer, and then we are going to incorporate them into a full cell to test, because a lot of things, engineering issues also happens when you incorporate things together. It's not just about the science, also about engineer, because you have your anode, you have cathode and membrane, you put them together, you have no idea what actually happened on the interface. And it is so different from what we test in the lab using the 3-electrode system. That's so different. So a lot of things we need to resolve. We are on the way, and we already solved a lot of problems. I think it should have a promising future.
Yeah, it sounds amazing, and that made me think of just kind of this. It's the scaling up part of it, right? We're going from the lab scale where we have small scale production. You're figuring out the science behind it. Now we're talking about the engineering part of it to see if we ramp this up and we make it bigger and we try to produce more, is it still going to work the same way it did at the lab scale? And that's a big step forward, because once you reach that stage, then it can be ready for market, and it can be something that we can really start implementing worldwide.
Yes. Yeah, because like the cell we use is only 5 centimeters square centimeter, but actually in industry that could be 100 square centimeter or even larger, and the tens of these unit cells stacked together to produce the hydrogen in high quantities, and that's so different from the lab scale. So you never know that is the current density distribution uniform on the big in the big unit, or like comparable to the small one. You never know. But if they are not uniform, then it creates a lot of issues. So yeah.
Well, it's super exciting what you're doing. I think we at New Hydrogen, obviously, we're super excited about your progress. We're excited to bring this forward to the world and let them see what you're doing, and hopefully we'll get together. We'll get to the point where we can be using whatever feedstock we want to, creating this clean green hydrogen that that can fuel the world in many different ways, from food production to heavy industry, transportation, and other sectors where it's been really hard to do up until this point. And so thank you for your great work. Any final comments you wanted to make before we wrap it up?
Uh,
You don't have to. Totally fine.
okay.
Totally. Well, it's been a pleasure talking with you. Thank you so much for your time. Thanks for all your hard work again. And we look forward to seeing the progress in the future.
Okay. Thank you so much.
Thank you. Take care. Have a good day.
Have a good day.